Hello, my name is Zan Bukhari, Bio 201 and 202 TA for Tempe, and today I'd like to talk to you about enzymes. So first off, let's talk about what an enzyme is, and then discuss some of its chemistry, go into the thermodynamics and kinetics of enzymes and the reactions they catalyze, and then use an example to talk about function and activity, and finally talk about your enzymes lab for Bio 201. So first off, what is an enzyme? Enzymes are biological catalysts. They're typically proteins. They end in ACE, A-S-E, and not all catalysts are enzymes, but all enzymes are some sort of catalyst. Sometimes they're nucleic acids, but for Bio 201, we just want to focus on proteins. Like we have our human salivary alpha amylase here, and notice how it's not a linear molecule. Specifically, notice how it's folded into a specific shape. So this three-dimensional shape that proteins have is known as tertiary structure, and it's very important to enzyme function. Let's talk about the biochemistry of an enzyme. So if we want to break a stick, and that would be a catabolic reaction, if we have a metal stick and we want to snap it into two broken sticks, we are breaking down something into its component parts. We are undergoing a catabolic reaction. This is as opposed to an anabolic reaction, which creates compounds from their component parts. Okay, so metal sticks don't tend to break on their own. You don't really see that happening. But hypothetically, if a metal stick, let's indicate it with an S for a substrate or a reactant of the reaction, were to snap into broken sticks, we'll call those the products, it would have to go through this in-between phase between a metal stick and broken sticks that we call the transition state, which is a bent stick. We'll indicate that with substrate double dagger, S double dagger. If we want to catalyze this stick breaking, we need a stickase, or a stick breaking enzyme, if you will. So a poorly evolved stickase would bind the substrate using these magnets. Why do I say this is poorly evolved? Because once it binds the substrate, it doesn't let go. It's bonded the metal stick, it doesn't make the reaction go, and it will never let the actual stick diffuse away from its active site. We say that this enzyme is too complementary to the substrate. We don't want the enzyme's active site to fit the substrate perfectly. We want it to fit the transition state perfectly so that the reaction can go and it won't sit there binding the products forever. It will allow the products of the reaction to diffuse away. So an effective stickase enzyme, we can see here the substrate's coming in. We have E plus S, and it doesn't bind it perfectly like this poorly evolved enzyme. However, it binds the substrate such that the transition state, the bent stick, fits in there perfectly. Now, bent sticks aren't very stable. Once you bend a metal stick, it's going to snap. So the reaction goes, and you end up with products. However, because the enzyme is shaped to fit the transition state very well rather than the products can easily diffuse away. And that's basically how the biochemistry of enzymes works. Okay, so now that we talked about the biochemistry of enzymes, let's discuss the thermodynamics and kinetics. I know we're going to get a bit technical here for a second, but it won't be too bad, I promise. So here we have our stickase again, the enzyme plus the substrate coming in. We have the enzyme substrate complex going into its transition state here. The stick is bent. And then we have the enzyme and the products diffusing away. So the stick has broken and the broken sticks are leaving. We can model the actual changes in energy involved with this reaction using what's called a free energy diagram here. So this G, the Gibbs free energy, shows that all the bonds holding this metal stick together have a certain fixed level of energy associated with them. And all the bonds holding these broken sticks together have another energy associated with them. And because this is a catabolic reaction, we can see that breaking this stick, the substrate, into the two broken sticks, the products, involves a drop in energy. We say when this start to end distance is negative, it's an exergonic reaction. Now, notice that where you start and end is indicated by the free energy of reaction. If you ever took a chemistry class, you probably calculated this. I should say right away that this is a thermodynamic quantity. It's only concerned with where you start and where you end. It doesn't care about how you got from point A to point B. And enzymes cannot change this. You will always start at this level for this substrate, and you will always end at this level for the products. What enzymes affect is kinetics. So the kinetics is how you get from point A to point B, how you get from substrate to products. And if we didn't have an enzyme, we can see there's a huge amount of energy that has to be put in to the system in order to get the stick to break. Okay, that makes sense. Sticks don't break spontaneously. But with our stickase here, this activation energy is depressed to a lower level. The hump is lowered. So if you imagine a whole bunch of balls here on the substrate side, it would take quite a bit of effort and quite a bit of energy in order to get one to bounce all the way over that black hump. However, with our lowered activation energy using the stickase, the balls would have a lot easier time bouncing over this lower free energy of activation and getting to the product side. Specifically, the stickase lowers the activation energy by what we call the binding energy here in pink. And that's the energy that the enzyme uses to bend this metaphorical stick. Now, with the stickiness transition state, the activation energy barrier is much smaller, as you can see here, and the reaction will go a lot easier, even though the distance from start to finish hasn't changed at all. Okay, so now that we've discussed thermodynamics and kinetics of enzymes as well as their biochemistry, let's use an example. So if we have this lovely toothpick case, looks like a pair of gloves, call that the enzyme, and our toothpicks are the substrate, let's start it out at a temperature T non. And so this is going to be the optimal temperature of our enzyme. So the enzyme binds the substrate, forms that enzyme substrate complex, and the toothpick is just about to snap, and it snaps. The enzyme is bound to the products and it's going to release them and return to its native conformation. Okay, everything's working fine. Now, if we decrease the temperature, let's say we put the enzyme on ice, then notice how the binding is slower. The enzyme can still bind the substrate and it still forms an enzyme substrate complex. It's in the transition state, reaction goes, and then the product will be released, the enzyme will return to its native conformation. But the lower in temperature you go, as we can see, I've circled in red on this graph here, the enzyme activity will decrease in a linear fashion. So, as you increase temperature up until the optimal temperature, enzyme activity increases linearly. However, what happens if we go beyond the enzyme's optimal temperature? If we heat the enzyme up really hot, or if we add acid or base to the enzyme to alter the pH of the solution it's in. Remember, pH 7 is neutral, above that is basic, below that is acidic. So here we have our enzyme, and see, it's getting kind of jumbled because we're above the temperature called the denaturation temperature, or our pH is out of the enzyme's optimal range. Okay, well, if we add substrate, the enzyme can't really bind the substrate. Its active site has changed shape. Before, the enzyme, pun intended, fit the toothpick like a glove, like a really good handshake. We call that induced fit. However, now that the active site is shaped differently, that induced fit is gone and the enzyme has denatured, we say. Okay, so it's all bent out of shape, it's all denatured, it's not going to bind the substrate anytime soon because of the three-dimensional shape being perturbed. And I should note that if you work in biotechnology, this is why you will frequently keep enzymes on ice. Because looking at this graph here, if the temperature is low, then the enzyme's activity is just decreased a bit. At the optimal temperature, the enzyme's activity is highest, sure, but as soon as you increase the temperature beyond that of denaturation, it gets all jumbled. And see how the fingers of these gloves are all tied together and they're a mess that can't be sorted out very easily? When you denature an enzyme by heating it or by altering the pH in either direction, there's a chance that the enzyme will never regain its original level of catalytic activity. And because enzymes are often expensive, we don't want that to happen in the lab because we want our enzymes working at peak efficiency. Now let's talk about your Bio 2-in-1 enzymes lab. So we have our two enzymes here, alpha amylase and amyloglucosidase. Now we're not in the lab anymore, we're in the body. So alpha amylase is located in the mouth, and it catalyzes the breakdown of amylose into maltose. Remember that catabolic reaction. Maltose is glucose bonded to glucose, and then amylose is this long branched starch molecule that has all of these glucose monomers in it. What do you think would be the optimal temperature and the optimal pH of alpha amylase? Now, I won't give you the answer, but I'll tell you that the mouth is open to the outside of the body, and the pH of saliva is approximately 7.0 to 7.5, so it's slightly basic. As for amyloglucosidase, it's located in the small intestine. It catalyzes the breakdown of maltose, so glucose bonded to glucose, into just individual glucose monosaccharides. What would be its optimal temperature and optimal pH? And I will tell you that the pH of the contents of the small intestine is approximately 8.0, so basic. Now think about what happens if you add hydrochloric acid to a solution of either of these enzymes. And hydrochloric acid's pH is somewhere between 3.01 and 0 depending on its concentration. So bear in mind, what happens to an enzyme when its pH of the surrounding solution is changed outside the optimal range? So I hope this has made the topic of enzymes easier for you to understand. Thank you, and good luck on your lab.